Betelgeuse has already exploded. Perhaps, but we simply do not know it yet. Right now, as you listen to these words, a light wave from the most magnificent cosmic firework in human history may be rushing toward us through the void. It has already crossed 649 light-years out of 650. 1 light-year remains. 1 year until the moment when night turns into day and a second sun flares up in the sky. The red supergiant in the shoulder of Orion is not just a bright dot in the winter sky. It is a cosmic bomb whose timer could go off at any second, or already went off 650 years ago, when the 100 Years' War was raging on Earth and the discovery of America was 40 years away. Back then, in the 1370s, the core of the giant could have collapsed into a point, ejecting energy into space capable of outshining an entire galaxy. And this wave of fire is flying toward us now. We live in a state of suspense, not knowing whether we will see the most magnificent cosmic show in the observable history of the universe tomorrow, or if it will happen in 1,000 years, when our descendants are no longer here. But there are signs. Strange, alarming signs. The star has begun to behave unpredictably. It dims, flares up, pulses as if. Scientists stay awake at night, pointing telescopes at the hunter's shoulder, trying to decipher the death throes of a dying giant. Because when Betelgeuse explodes, it will not just be a beautiful sight. It will be an event that rewrites our understanding of the cosmos and our place in it. If you are interested in learning what lies behind this mystery and why scientists are so excited, support the channel with a subscription and a like. We explore the most fascinating mysteries of space every week, and ahead of us is a journey to a dying star that could change our sky forever. People have looked at Betelgeuse for thousands of years, not knowing what they were seeing before them. For the ancient Greeks, it was the arm or shoulder of the mighty hunter Orion, a giant whom the gods raised to the sky. Arabic astronomers called it Yad al-Jawza, the hand of the central figure. Over time, this name was transformed and distorted through translations and recopying, turning into the word we know today, Betelgeuse. Try to say it out loud. Feel how the tongue stumbles over these syllables. Betelgeuse. In this name, one hears something ancient, alien, like an echo of distant civilizations that also tilted their heads back to the stars and tried to find meaning in the shimmering dots of light. The Chinese included it in the constellation Shen, which represented a legendary warrior. The Indians of North America saw various figures from their mythology in the bright stars of Orion. Every culture, every people who looked at the night sky noticed this reddish star and gave it meaning. It was too bright, too noticeable to ignore. Its reddish hue set it apart from its white and blue neighbors. The ancients could not have known that this light was a sign of dying, that they were observing the final breath of a cosmic giant stretched over millennia. When Renaissance astronomers began to systematically catalog the stars, Betelgeuse received the designation Alpha Orionis, although in brightness it often yields to Beta Rigel. This strange discrepancy occurs because the brightness of Betelgeuse changes. It is not constant like most stars. It breathes. It swells and contracts, becoming now brighter, now dimmer. Ancient astronomers noticed this variability but could not explain it. They simply recorded it. Sometimes this star shines more strongly, sometimes more weakly. The reasons remained a mystery. In the 19th century, a real hunt for understanding the nature of stars began. Spectroscopes appeared, instruments that decompose light into its components. Astronomers pointed them at Betelgeuse and saw something amazing. The spectrum showed absorption lines characteristic of a cold star. Cold by stellar standards, of course, the surface temperature was only 3,000 degrees. For comparison, the surface of our sun is heated to 6,000 degrees. Betelgeuse turned out to be colder, and that is precisely why it is red. Hot stars glow blue or white, cold ones glow red or orange. It is like a flame. The hottest part of it is blue. At the base, where the temperature is lower, the tongues of flame are orange and yellow. But a cold star is only half the trouble. At the beginning of the 20th century, astronomers learned to measure the sizes of stars. And when they pointed their new methods at Betelgeuse, the results shocked them. This star was monstrously large. If placed in the position of our Sun, its surface would reach the orbit of Jupiter. Imagine, instead of a small dot in the center of the solar system, a huge red ball swallowing Mercury, Venus, Earth, Mars, and even giant Jupiter would be inside this monster. Everything we consider our cosmic home, all the planets where life could theoretically exist, all of this would disappear inside a single star. Such stars received the name red supergiants. Supergiants because they are incredibly large, red because they are cold and glow with red light. But behind these calm scientific terms lies a drama. A red supergiant is an unstable state. It is an agony. These are the death throes of a star that has exhausted its resources and is now bloating, trying to prolong its existence for at least a moment by cosmic standards. Betelgeuse is dying. It is dying right now before our eyes, although we see it as it was 650 years ago. Astronomers of the 20th century began to understand what happens inside such stars. They built models, calculated equations, conducted thousands of computer simulations. The picture that opened before them was simultaneously beautiful and terrifying. Inside the red supergiant, a thermonuclear war is taking place. In the center, in the core, where pressure and temperature reach unimaginable values, hydrogen atoms fuse into helium, releasing colossal energy. This is the same process that occurs in our Sun. But the Sun will burn hydrogen for billions of years more. Betelgeuse has already run out of hydrogen in its core. What happens when a star exhausts its hydrogen? It does not go out immediately. Instead, a new stage begins. The core, now consisting of helium, begins to shrink under its own weight. The compression heats it even more until the temperature becomes sufficient for the next reaction. Helium begins to fuse into carbon and oxygen. Simultaneously, hydrogen continues to burn in a shell around the core. The star seems to receive a new life, but this life comes at a high cost to it. The energy released during helium synthesis is enormous. It is so great that the outer layers of the star are literally thrown outward. The star swells. Its radius increases hundreds of times. Imagine a balloon into which air continues to be pumped. The rubber stretches, becomes thinner and thinner. The balloon becomes larger and larger. So it is with the star. Its outer layers stretch out, thin out, cool down. That is why it becomes red. But this is not the end. When the helium in the core runs out, the process repeats. The core shrinks again, heats up, and the next stage of synthesis begins. Carbon and oxygen fuse into heavier elements: neon, magnesium, silicon. With each stage, the core becomes hotter, reactions go faster, but the fuel lasts for less and less time. The star is like a sprinter who initially ran a marathon at a steady pace, but now, in the final meters, gives everything, burning the last of its strength in a matter of seconds. Inside Betelgeuse now is a multi-layered structure similar to an onion. In the center is a red-hot core of iron and nickel. Around it is a shell where silicon turns into iron. Further out is a layer where oxygen is synthesized into silicon, and so on. Layer after layer until we reach the outer shell. Huge, rarefied, where hydrogen is still burning. This onion is unstable. The layers mix, convect, bubble like water in a pot on a stove. Huge bubbles of red-hot gas rise from the depths to the surface, then cool and sink back down. The entire star trembles, pulses, changes shape. If we could see its surface in detail, we would notice that it is not round. It is asymmetrical, bloated in some places, indented in others. This dying giant writhes in agony. Why iron? Why does everything end specifically with iron? The fact is that iron is the limit. Before iron, every synthesis reaction releases energy. The fusion of hydrogen into helium gives energy. The fusion of helium into carbon gives energy, and so on up to iron. But the fusion of iron into heavier elements does not release energy. On the contrary, one must expend energy for this. Iron is the point of equilibrium, a dead end for thermonuclear synthesis. When iron accumulates in the core of a star, thermonuclear reactions stop, and then the finale begins. The core of Betelgeuse may now already consist of iron or be close to it. We cannot look inside the star, cannot measure what is happening there in the center under layers of plasma hundreds of millions of kilometers thick. We can only build models, calculate, and assume. Models say that a massive star spends a relatively short time at the red supergiant stage by cosmic standards. Millions of years, a drop in the ocean compared to the billions of years of life for smaller stars. But for us humans, 1,000,000 years is an eternity. Civilization has existed for several thousand years. Humanity in its modern form for several 100,000 years. 1,000,000 years ago, our ancestors were just learning to use fire. Betelgeuse could explode tomorrow or in 100,000 years. Or, what is most eerie, it has already exploded, and the light from the explosion is already on its way. The distance to Betelgeuse is about 650 light-years. This means that the light we see today left the star in the 14th century, in 1370 to be more precise. Europe was then suffering from the Black Death, a plague epidemic that wiped out a third of the population. China was experiencing the decline of the Yuan dynasty. The Aztecs were only beginning to build their empire in Central America. It was at that time that the photons that enter our eyes today broke free from the atmosphere of Betelgeuse and rushed into the cosmic void. If the explosion occurred in the 14th century, we will find out about it only now. If it occurred in the 15th, we will find out in 50 years. If in the 13th, we should have already seen it, but we do not, which means there has been no explosion yet. Or there was, but later. We live in a state of uncertainty, not knowing when the news will arrive. And the news will not arrive the way we are used to. Usually we learn about cosmic events from reports by scientists, from articles, from news. First, astronomers discover something in their telescopes, then analyze the data, then publish the results, and only then do we, ordinary people, read about it. But the explosion of Betelgeuse will be different. Everyone will see it at once. No telescopes will be needed, no observatories. Just step outside at night and look at the sky. In the constellation of Orion, where a reddish star used to shimmer, a new point of light will flare up. At first, it will be the size of an ordinary star, but with every hour it will become brighter, brighter, and brighter. In a few days, it will reach the brightness of a full moon, and perhaps even surpass it. Imagine, you step out of your house in the morning, and there are two suns in the sky. One is the familiar yellow one in the east. The second is smaller but still blindingly bright, where the constellation of Orion should be. During the day, you can see both of these points of light. At night, the new star illuminates the earth so that one can read a book without a flashlight. The shadows from it are sharp and clear. The sky is not black, but dark blue, as if in deep twilight. This will last for weeks, maybe months. Gradually, the new star will dim, but even a year after the explosion, it will still be visible to the naked eye. A bright dot where Orion used to be. But before that moment, events will occur that we will not see, but will learn about, thanks to science. A few hours before the flash becomes visible, neutrino detectors all over the world will start going crazy. Neutrinos are ghostly particles that almost do not interact with matter. They pierce the Earth right through, fly through our bodies by the billions every second, and we do not feel it. Neutrinos are born in thermonuclear reactions in the center of stars and instantly fly outward without delay. Light from the center of the sun takes thousands of years to make its way to the surface, wandering in the thickness of the plasma. Neutrinos fly out immediately. When the core of Betelgeuse collapses, at that moment so much energy is released that most of it is carried away specifically by neutrinos. They burst out of the collapsing core and rush at the speed of light in all directions. A few hours after the collapse, they will reach Earth, and detectors will record this. Scientists will see a sharp spike on the graphs. They will understand that what has been awaited for decades has happened. A supernova, and it is close. So close that the detectors will literally be overwhelmed by the number of neutrinos. An alarm will be declared. All over the world, astronomers will begin to point telescopes at Orion, waiting to see the flash, because light travels more slowly. More precisely, light travels at the same speed as neutrinos, but it needs time to break out from inside the star to the outside. The core collapse happens in the center. The shock wave moves from the center to the surface. Only when it reaches the surface will the star flare up. This will take hours. Therefore, humanity will have a small window, a few hours between the detection of neutrinos and the visual flash. A few hours to prepare, to set up instruments, to notify the world. This is happening. Neutrino detectors are scattered all over the world. They are hidden deep underground, in mines and tunnels, where cosmic rays and other interference do not hinder the catching of these elusive particles. One of the largest is located in Japan, in an abandoned mine under a mountain. It is a huge reservoir of pure water surrounded by thousands of sensitive sensors. When a neutrino occasionally collides with an atom in the water, a flash of light occurs, which the sensors record. Usually these are rare events, a few a day perhaps, but when the neutrinos from the supernova reach Earth, there will be billions of them. In a few seconds, the detector will record thousands of collisions. It will be like hail drumming on a roof. It is impossible to be mistaken. The system will automatically send an alarm signal to all the world's observatories. Astronomers have already agreed among themselves. When this signal arrives, everything else is canceled. All telescopes turn to the coordinates from which the neutrinos came. The observation of the most magnificent cosmic event in human history begins. Now let us understand exactly what happens at the moment of the explosion. Why the star explodes, what triggers this cataclysm. To understand this, one must imagine the internal structure of the star in its final moment. The core consists of iron and nickel. It is approximately the size of Earth, but has a mass 1.5 times that of the Sun. Imagine a ball the size of our planet, but so dense that its mass exceeds the mass of an entire star. Every cubic centimeter of this substance weighs tons. This is not just the density of metal. This is matter compressed by gravity to a state in which atoms are literally right up against each other. Inside this core, a constant struggle is going on. On one hand, gravity is trying to compress the core even further. The huge mass of the outer layers presses from above, striving to crush the core into a point. On the other hand, the pressure of degenerate electrons resists. This is a quantum mechanical effect. Electrons cannot occupy the same state. They repel each other at the micro level, creating pressure that holds the core from collapse. While thermonuclear reactions are going on in the core, additional energy is released, which also helps resist gravity. But when iron accumulates, reactions stop, energy is no longer released, only electron pressure remains, and it begins to lose the battle. The mass of the outer layers presses harder and harder. The core slowly shrinks, density grows, temperature also grows, but this no longer helps. There is no fuel for reactions, and suddenly something catastrophic happens. At a certain density, iron begins to fall apart. The nuclei of iron atoms decompose back into protons and neutrons. This requires energy, enormous energy. Where does this energy come from? From the kinetic energy of particles, from heat. The core suddenly cools down, pressure drops, and it is like pulling the plug out of a dam. Gravity instantly wins, the core collapses. Imagine that the entire ball the size of Earth shrinks to the size of a city in a fraction of a second. 1 second, and the core decreases thousands of times. Density soars to unimaginable values. Protons and electrons are squeezed so hard that they fuse, turning into neutrons. A neutron star arises. A ball of pure neutrons so dense that a teaspoon of its substance would weigh billions of tons. Or if the mass of the core is large, the collapse does not stop even there, and the core continues to shrink until it turns into a black hole. But at the moment of collapse, so much energy is released that it is enough to tear the entire star apart. Why? When the core collapses, it literally bounces back. Neutron matter is incredibly stiff. The collapse stops abruptly, and a shock wave is formed that rushes outward at a speed of tens of thousands of kilometers per second. This wave slams into the outer layers of the star, heats them, tears them apart, and ejects them into space. Simultaneously, a huge number of neutrinos, born during the transformation of protons into neutrons, also carry away energy. Part of this energy is transferred to the matter, further accelerating the shock wave. The outer layers of the star literally evaporate. They fly apart in all directions, forming an expanding shell of red-hot gas. This shell glows. It is heated to millions of degrees. There is so much energy that the flash outshines an entire galaxy. If the explosion of Betelgeuse occurred in our galaxy, but at its other end, we would still see the flash with the naked eye. But Betelgeuse is in our backyard, only 650 light-years away. This is a neighboring star by cosmic standards. There are hundreds of billions of stars in our galaxy. Most of them are much further away. Betelgeuse is one of the closest massive stars ready to explode. And when it happens, we will have a front-row seat to the most magnificent show in the universe. What will people on Earth see? First, as already mentioned, neutrino detectors will go off. Scientists will sound the alarm, but most people will not find out about it immediately. News will spread through scientific circles and the internet, but not everyone follows astronomical events in real time. And a few hours after the neutrino burst, someone, looking at the night sky by chance, will notice a new star. It will be bright, very bright. Brighter than Venus, brighter than Jupiter. In the few minutes while the person watches, it will become even brighter. He will call others. People will come out into the streets. A storm will begin on social media. Photographs of the new star will fill the internet. Everyone will ask, "What is this? Where did it come from?" Astronomers will answer, "Betelgeuse. It has exploded. It is a supernova." The brightness will grow for several days. The flare will reach its peak about a week after the start. By this moment, the supernova will shine with the brightness of a full moon, perhaps even brighter. Some models predict that it may become visible even during the day, like a faint star against the background of the blue sky. At night, it will dominate. All other stars will seem dim compared to it. The constellation of Orion will change forever. Instead of the reddish shoulder of the hunter, there will be a dazzling white dot outshining everything around it. But this will not last forever. After a few weeks, the brightness will begin to fall, at first slowly, then faster. In a month, the supernova will still be visible to the naked eye, but no longer as bright. In 3 months, it will look like an ordinary bright star. In half a year, it can only be seen through binoculars, in a year only through a telescope. And after several years, a nebula will remain in its place, an expanding cloud of gas, the former outer layers of the star, now scattered in space. In the center of this cloud, invisible to the eye, will be a neutron star or a black hole, all that remains of the once mighty giant. But while the supernova shines, it will be an object of the most intense study. All telescopes on Earth and in space will turn toward it. Astronomers will take spectra every hour, tracking how the composition of light changes. They will look for traces of various elements that were synthesized during the explosion. Because a supernova is not just destruction, it is creation. At the moment of explosion, temperature and pressure become so high that reactions begin which are impossible under normal conditions. Heavy elements that could not form in the thermonuclear reactions of a star are born in the fire of the explosion. Gold, platinum, uranium, all elements heavier than iron, are created specifically in supernovas. Every atom of gold in your jewelry, every atom of uranium in nuclear fuel was once synthesized in the explosion of a dying star. We are literally made of stardust, and the explosion of Betelgeuse will remind us of this. Scientists will be able to trace the entire process in real time. They will see how the shell expands, how its temperature changes, how various elements appear in the spectrum. They will be able to test their theories, to calibrate models. Until now, we have observed supernovas only in distant galaxies. There they look like faint dots of light. They are difficult to study in detail, but Betelgeuse will be so close that we will see details that were previously inaccessible. This will be a scientific breakthrough. The data collected during the explosion will be analyzed by scientists for decades. This event will enter textbooks and become a reference point in astrophysics. And what about the danger? Many have heard horror stories that a supernova explosion could destroy life on Earth. How real is this in the case of Betelgeuse? Let us find out. A supernova is indeed dangerous. It releases an enormous amount of energy in the form of radiation and high-energy particles. If such an explosion occurred close to Earth, the consequences would be catastrophic. Hard radiation, gamma rays, X-rays would destroy the ozone layer protecting us from ultraviolet. Cosmic rays accelerated by the explosion would bombard the atmosphere, causing mutations and destroying microorganisms. In Earth's past, there may have been mass extinctions caused by nearby supernova flares, but the key word here is nearby. How close must a supernova be to pose a threat? Scientists estimate the critical distance at about 100 light-years. If the explosion occurs closer, it is a serious problem. If further, we are safe. Betelgeuse is located 650 light-years from us. This is 6 times further than the critical distance, far enough not to fear catastrophic consequences. Yes, we will receive a dose of radiation. Satellites will record spikes of gamma rays and X-rays. But the atmosphere will protect us. It will absorb most of the hard radiation. Only a small addition to the natural background will reach the surface, no more dangerous than an extra X-ray at a clinic. But there is another factor: gamma ray bursts. These are narrow, directed jets of radiation that can accompany some supernovas. If the rotation axis of a collapsing star is pointed at us, and if a jet, a stream of high-energy radiation, forms along this axis, then even at a great distance it could be dangerous. Gamma ray bursts are some of the most energetically powerful events in the universe. They can be fatal at distances of thousands of light-years. But the good news is that the rotation axis of Betelgeuse is not pointed at us. Scientists have measured this using interferometry, observing the distribution of material around the star. We are off to the side. Even if a gamma ray burst occurs, it will pass us by. We will see the flash, but we will not receive a fatal dose. So the explosion of Betelgeuse will be safe. It is important to understand this, because when it happens, rumors, panic, and conspiracy theories will begin to spread. Someone will say it is the end of the world, that radiation will kill everyone, that governments are hiding the truth. Do not believe it. Scientists honestly say, yes, this is a magnificent event, but no, it does not threaten Earth. We are at a safe distance. The only thing that will change is the night sky. And this change will be beautiful, not dangerous. However, the behavior of Betelgeuse itself in recent years adds intrigue. At the end of 2019, astronomers noticed something strange. The star began to dim. At first, it was unnoticeable. Betelgeuse always changed its brightness. It is a variable star. But the usual changes were predictable, cyclical. 2 main pulsation periods were superimposed on each other. One lasted about 400 days, the other about 6 years. Astronomers learned to predict when the star would be brighter and when dimmer. But at the end of 2019, the brightness fell more than expected, much more. By February 2020, Betelgeuse had dimmed by more than 2 times compared to its usual brightness. It was visible even to the naked eye. People familiar with the winter sky noticed that the shoulder of Orion had become noticeably paler. Astronomers sounded the alarm. Is this it? Is the star preparing to explode? Feverish activity began. Telescopes from all over the world were pointed at Betelgeuse. Observations were conducted in different ranges: visible, infrared, ultraviolet. Everyone wanted to understand what was happening. Theories multiplied. Some scientists said it was a sign of imminent core collapse. Perhaps internal processes had accelerated and the star was entering the final stage. Others suggested it was just an unusually strong pulsation, a superimposition of several cycles. Still others put forward the idea that the star had ejected a cloud of dust that was temporarily obscuring it from us. The debates were heated. Scientific articles came out one after another, each with a new interpretation of the data. And then, as suddenly as it began, the dimming stopped. By April 2020, Betelgeuse began to regain its brightness. By summer, it was almost at its usual level. Many breathed a sigh of relief. False alarm. Others, on the contrary, were disappointed. They wanted to see the explosion, if only for scientific interest. But what actually happened? Analysis of the data showed that most likely the star had indeed ejected a huge cloud, which then cooled, turned into dust, and partially blocked its light. This was confirmed by observations in the infrared range, where dust glows with its own radiation. High-resolution images showed an asymmetrical distribution of brightness on the surface of the star. One half was brighter, the other dimmer. This corresponded to the model of a dust cloud moving along the line of sight between the star and us. But why did this happen? Red supergiants periodically eject matter. Their surface is unstable. Huge convective cells lift hot material from the depths, which can then be thrown into space. Stellar wind carries away mass at a rate equivalent to the mass loss of Earth every year. Imagine, every year Betelgeuse loses as much material as is contained in an entire planet. This material forms a nebula around the star, which can be observed in a telescope. But sometimes the ejections are on a larger scale. A huge bubble of plasma bursts from the surface, cools, and dust particles condense in it. Tiny solid particles consisting of carbon, silicon, and other elements. This dust absorbs the star's light, making it dimmer for an external observer. So the great dimming of 2019 was likely not a precursor to an immediate explosion. It was the usual, albeit large-scale activity of a dying giant. But this event itself reminded us how unstable Betelgeuse is, how close it is to the finale. Normal stars do not behave this way. Our sun has shone stably for billions of years and will shine for billions more. Its brightness changes by fractions of a percent. Betelgeuse, however, thrashes like a dying beast. It throws itself from side to side, ejecting pieces of itself into space. These are signs of agony. After 2020, observations continued. The brightness of Betelgeuse returned to normal, but astronomers did not relax. They continue to monitor the star constantly because no one knows when the finale will occur. Models of stellar evolution give a wide range from several thousand years to 100,000 years. This is a huge uncertainty. Why is it so difficult to predict? The fact is that the processes inside massive stars at the final stages are incredibly complex. Everything there depends on details: exact mass, rotation speed, magnetic fields, convection, mass loss. Small changes in these parameters can move the moment of collapse tens of thousands of years forward or backward. And many of these parameters we cannot measure accurately. We cannot weigh the core of a star, cannot measure the temperature in the center. We build models based on what we see from the outside and extrapolate inward. It is like trying to understand what is happening inside a closed pot on a stove by observing only the steam coming out from under the lid. One can make reasonable assumptions, but the accuracy is limited. Nevertheless, there are signs that could suggest the end is approaching. For example, if the brightness began to change more chaotically, if pulsations became irregular, this could indicate internal cataclysms. If the star began to lose mass faster, ejecting more and more matter, that too would be an alarming sign. Some models predict that shortly before collapse, a red supergiant may temporarily shrink, becoming hotter and bluer, and then expand again. If we saw such behavior in Betelgeuse, it would be a strong hint. Another way to learn about an approaching explosion is neutrino detectors, but there is a nuance here. Neutrinos that are born in ordinary thermonuclear reactions in the core of a star we cannot detect at such a distance. There are too few of them. We detect neutrinos from the Sun because it is close. Betelgeuse is hundreds of times further away, and its neutrino flux from ordinary reactions is too weak. But if the core begins to collapse, the neutrino flux will increase sharply by many orders of magnitude. These are the neutrinos we will see. Но это будет уже в момент коллапса, за несколько часов до видимой вспышки. There will be no advance warning. Betelgeuse will explode without a preliminary call. We will find out about it only when it happens. That is precisely why scientists monitor the star so closely. Every unusual behavior is recorded, analyzed, compared with models, and patterns are sought. Perhaps in this data is hidden the key that will allow us to predict the explosion at least a few weeks or months in advance. Perhaps not. Но сам процесс наблюдения, накопления данных уже ценен, потому что когда взрыв произойдет, эти данные помогут понять, что именно предшествовало катастрофе. Astronomers of the future studying the archives will say, here, 6 months before the explosion, such and such happened, and we did not give it significance. Or they gave it significance but did not understand it correctly. Science works like this. We learn from events, build better models, and next time we predict more accurately. But let us return to the explosion itself, and to what will remain after. When the expanding shell of the supernova cools and becomes transparent, we will see a nebula. It will be one of the most beautiful nebulas in the sky. Like the Crab Nebula, the remnant of a supernova that flared up in 1054 and was observed by Chinese astronomers, or like the nebula in Cassiopeia, the remnant of another recent supernova, Betelgeuse will leave its mark. An expanding cloud of gas glowing in various colors thanks to radiation from internal processes and from the central object. And what is there in the center? A neutron star or a black hole? This depends on how much mass remained in the core after the outer layers were shed. If the mass of the core is less than about 2 to 3 solar masses, a neutron star forms. This is a ball about 20 kilometers in diameter, consisting almost entirely of neutrons. The density is such that a teaspoon of the substance would weigh billions of tons. On the surface of a neutron star, gravity is billions of times stronger than Earth's. If you tried to stand on the surface of a neutron star, you would instantly be flattened into a layer 1 atom thick. But of course you will not get there. Long before that, tidal forces will tear you apart. Neutron stars often rotate rapidly. The conservation of angular momentum during collapse accelerates them to hundreds of revolutions per second. They emit beams of radiation along their magnetic poles. And if these beams are directed at us, we see a pulsar, a source that blinks with a very precise period. Perhaps Betelgeuse will turn into a pulsar, and we will be able to observe it, hear its radio signal, this cosmic lighthouse pulsing with incredible regularity. It will be the voice of a dead star, an echo of its past power. But if the mass of the core is too large, the collapse does not stop even at the stage of a neutron star. Gravity is so strong that no force can oppose it. The collapse continues, and the core shrinks into a singularity, a point of infinite density surrounded by an event horizon. A black hole is formed. This is no longer a star in the usual sense. It is a hole in space-time, a region from which nothing can escape, not even light. The black hole from Betelgeuse would be relatively small in mass, a few masses of the Sun, but still impressive, and it would continue to influence the surrounding space, warping it and attracting any matter that turned out to be too close. What exact outcome awaits Betelgeuse we will find out only after the explosion. By the character of the supernova glow, the light curve, and the spectra, scientists will be able to determine what remains in the center. If they record a pulsar, it will confirm a neutron star. If there is no pulsar, but there are signs of accretion, matter falling onto the central object with the release of enormous energy, this may indicate a black hole. One way or another, we will receive an answer to the question that currently remains open. And how will the explosion of Betelgeuse affect culture and society? This event will enter human history. It will become as significant as the discovery of America, the moon landing, or the invention of the internet, because it is a cosmic-scale event that everyone will be able to see with their own eyes. No telescopes are needed, no special knowledge. Just step outside at night and look up, and you will see something none of your ancestors saw in the entire history of humanity. A second sun in the sky, a star that exploded. This will inspire millions of people. Children who see the supernova will want to become astronomers. Artists will paint pictures, poets will write verses, and philosophers will share reflections on transience and eternity. Religious thinkers will see in this a sign, a symbol. Someone will say it is a harbinger of the end, someone else that it is the beginning of a new era. People will gather in groups to observe the phenomenon together. Astronomical societies will organize mass observations. Observatories will be overcrowded with visitors. The internet will explode with discussions, photographs, and videos. It will be a global event uniting humanity in a shared experience of a cosmic wonder. And it will remind us how small we are in the face of the universe. A star that existed for millions of years, which was a giant among stars, turned in a single moment into a cloud of gas and a tiny remnant. All its power, all its mass scattered in space. The energy it released in the milliseconds of the explosion exceeds all the energy humanity has used in its entire history. And this happened naturally, as part of the life cycle of stars. We live in a dynamic universe where something is constantly being born and dying. Stars ignite from clouds of gas, live, shine, and then die, returning material back into interstellar space. This material then participates in the formation of new stars and new planets. The cycle continues. We ourselves are part of this cycle. Every atom in your body was once part of a star. The carbon your cells consist of was synthesized in the core of a red giant billions of years ago. The oxygen you breathe was also born in a star. The iron in your blood was created in the final moments before a supernova explosion. You are stardust gathered into a conscious form. And when Betelgeuse explodes, it will create new atoms that perhaps, in billions of years, will become part of some other creatures, other life forms, other stories. This philosophical realization changes perspective. We are used to thinking of ourselves as the pinnacle of creation, as the center of the universe. But when you look at the explosion of a star, you understand that we are only a tiny episode in a magnificent cosmic drama. And there is nothing demeaning in this. On the contrary, it ennobles. We are part of something greater. We are connected to the universe at the most fundamental level. Our existence is possible only because other stars once died, creating the elements from which Earth and everything living on it were formed. Betelgeuse will remind us of this connection. There is another aspect worth considering. What if the explosion has already occurred? Remember that light travels to us for 650 years. Imagine that Betelgeuse exploded in the year 1500. Columbus has just discovered America. The Renaissance is in full swing in Europe. Leonardo da Vinci is painting his pictures, and in space, 650 light-years from Earth, a giant star is dying. Its core collapses, the shell explodes, and a flash of light rushes in all directions. But this light will reach Earth only after 650 years, that is now, or in the year 2150. We live in this uncertainty. Maybe right now, while you listen to these words, the light wave from the explosion is at a distance of 1 light month from Earth. In a month, it will arrive, and we will see the flash. Or it is at a distance of 1 light year. In a year, we will see it. Or the explosion will occur in 100 years. We will not see it, but our descendants will. Or in 1,000 years, 10,000, we do not know. And this knowledge, or rather this lack of knowledge, adds a special sharpness. We live in expectation. Every night could be the very night when a new star flares up in the sky. Astronomers joke that watching Betelgeuse is like waiting for a balloon to pop. You know it will pop, but you do not know when. You can sit and look at it for hours, and nothing happens, or you can turn away for a second, and at that moment, pop. So it is with Betelgeuse. Scientists have observed it for decades, and it stays in place. It blinks, it changes, but it does not explode. And then, one fine day when no one expects it, it will flare up. And the astronomers who spent their whole lives waiting for this moment will either be the first witnesses or will find out about it from the news, having slept through the most important event of their careers. That is precisely why an automatic monitoring system has been created. Robot telescopes scan the sky every night, measuring the brightness of thousands of stars. If the brightness of any star changes sharply, the system will automatically send notifications. Astronomers are subscribed to these notifications. They will receive a message on their phones. Betelgeuse has flared up, and then the race will begin. Everyone will want to point their telescope at the star first, to get the first spectra, the first data. It will be a competition but also cooperation at the same time, because a lot of data is needed. And the more telescopes observe, the better. Already there are plans for coordinated observational campaigns. Astronomical organizations all over the world have agreed that when Betelgeuse explodes, these telescopes will do this, and those will do that. Someone will take optical spectra, someone infrared, someone X-rays from space, someone will track neutrinos, someone gravitational waves. Yes, gravitational waves can also be detected if the explosion is sufficiently asymmetrical. Modern gravitational wave detectors, such as LIGO, are theoretically capable of catching a signal from a nearby supernova. It would be the first case of simultaneous detection of light, neutrinos, and gravitational waves from a single event, a true triumph of multi-messenger astronomy. And all this data, all these observations, will give us unprecedented understanding of what happens during a supernova explosion. We will learn details that we could previously only assume. How exactly does the shock wave propagate? How do the star's layers mix? Which elements and in what quantities are synthesized? How is a neutron star or a black hole formed? How does the expanding shell interact with the environment? All these questions will find answers. Scientists will be able to test their models, see what they predicted correctly and where they were wrong, and based on this, build even more accurate models that will help understand other supernovas, more distant and more complex. But besides the scientific significance, the explosion of Betelgeuse will also have a symbolic one. It will become a reminder that the cosmos is not static. Stars are not eternal. Everything changes. Everything flows. Even giants die. And in their death there is beauty, because it gives life to the new. The gas and dust scattered by the explosion will become the material for new stars. Planets may form in these new stars. On these planets perhaps life will arise. and this life will exist thanks to the fact that Betelgeuse once died, enriching the cosmos with heavy elements. Death and birth are intertwined. One is impossible without the other. This thought should comfort us. Yes, we are mortal. Yes, everything we know will one day disappear, but the matter of which we consist will continue to exist. It will take other forms, enter other structures. The atoms of your body will someday become part of stars, planets, maybe other living beings. In this sense, we are immortal, not as individuals, but as part of the matter of the universe. And Betelgeuse, by exploding, will demonstrate this eternal cycle on a magnificent scale. Now let us go a little deeper into the details of what we will see in the spectrum of the supernova. When astronomers take the first spectra, they will see the lines of various elements. At first, in the first days, the spectrum will show hydrogen and helium. These are the outer layers of the star, which move the fastest and become visible first. The hydrogen lines will be wide and blurred because the gas moves at enormous speeds, thousands of kilometers per second. The Doppler effect blurs the lines. Part of the gas moves toward us, part away from us, and the lines shift to the blue and red sides respectively. After a few weeks, when the outer layers become more transparent, we will see deeper layers. Lines of oxygen, carbon, and silicon will appear. These elements were synthesized in the star even before the explosion during the process of normal thermonuclear reactions. Their presence will confirm that we are observing specifically the collapse of a massive star and not some other type of supernova. Because different types of supernovas exist, those that occur in massive stars are called Type II supernovas. They are characterized by the presence of hydrogen in the spectrum. Betelgeuse will yield precisely such a supernova. Over time, as the shell cools and expands, the spectrum will change. A few months after the explosion, we will see the lines of heavier elements: iron, nickel, and cobalt. These are elements that were in the core of the star or were synthesized during the explosion. Their radioactive decay will support the supernova's glow even after the shock wave cools down. Nickel turns into cobalt, cobalt into iron, and each decay releases energy that heats the gas and makes it glow. Astronomers will measure the expansion speeds of different layers and determine their mass and temperature. They will build a three-dimensional model of the explosion and show how the material is distributed in space. Modern computer simulations already provide approximate pictures, but real data will allow these models to be calibrated with unprecedented accuracy. We will find out how symmetrical the explosion is. Theory predicts that supernova explosions are often asymmetrical. Material is ejected unevenly. Clumps and jets are formed. This is related to convection and instabilities at the moment of the explosion. Observations of Betelgeuse will show if this is actually the case. Another interesting aspect is the interaction of the expanding shell with the environment. Around Betelgeuse, there is already a nebula created by the stellar wind over millions of years. When the shock wave from the explosion slams into this nebula, a bright flash will occur. The shock wave will heat the nebula's gas to millions of degrees, and it will begin to glow in the X-ray range. Space telescopes such as Chandra or future missions will observe this process. We will see how the wave propagates through the nebula, how it compresses and heats the gas, and how complex structures are formed: filaments, nodes, and rings. This interaction can also tell us about the mass lost by the star before the explosion. The denser the nebula around it, the more mass the star lost. By measuring the brightness and spectrum of the radiation from the interaction, astronomers will be able to estimate how much material was ejected by Betelgeuse in the last thousands and millions of years. This is important for understanding the evolution of massive stars. Mass loss affects what the final remnant will be: a neutron star or a black hole. The more mass lost, the smaller the core mass, the more likely a neutron star. Besides visible light, X-rays, and neutrinos, the explosion can be detected in other ranges as well. Radio waves, for example. When the expanding shell interacts with magnetic fields in the surrounding space, charged particles are accelerated and emit synchrotron radiation, which is radio waves. Radio telescopes all over the world will listen to the supernova, tracking its radio brightness. This will provide information about the magnetic fields and the population of relativistic particles, electrons and protons accelerated to speeds close to the speed of light. Perhaps we will also discover gamma rays, but no longer from the explosion itself, but from the remnant. If a rapidly rotating neutron star with a strong magnetic field forms in the center, it can work as a giant particle accelerator. Particles accelerated in the magnetosphere of the neutron star will interact with the surrounding gas, creating gamma radiation. Space gamma-ray telescopes will be able to detect it. This will be evidence of the activity of the central object. And what about gravitational waves? As already mentioned, if the explosion is asymmetrical, a gravitational wave signal may arise. Gravitational waves are ripples in space-time propagating at the speed of light. They arise during the accelerated movement of massive objects. The collapse of a star's core is precisely such an event. If the core collapses unsymmetrically, forming, for example, an elongated or curved structure, this will create gravitational waves. Modern detectors such as LIGO and Virgo have already detected gravitational waves from the merger of black holes and neutron stars. Но от сверхновой пока не было обнаружено ни одного сигнала. Betelgeuse could be the first. The signal will be weak. The distance is still large by the standards of gravitational wave astronomy, but detectors are constantly improving. By the time Betelgeuse explodes, next-generation detectors with even greater sensitivity may be operational, and then we will have a chance to hear the gravitational whisper of a dying star. This would be incredible. Simultaneous detection of light, neutrinos, and gravitational waves from a single source would open a new era in astronomy. We could compare the arrival times of different signals and check if they all indeed move at the speed of light. As the theory of relativity predicts, we could extract information about the dynamics of the collapse, the shape of the core, and the physics of extreme densities and temperatures. All this information will change our understanding not only of supernovas, but also of fundamental physics. At the moment of collapse, the conditions in the star's core are such that matter is in states that cannot be reproduced in terrestrial laboratories. Densities higher than nuclear, temperatures in billions of degrees. In such conditions, laws of physics that we know only theoretically are at work. Supernova observations will provide an experimental check of these laws. For example, they will help clarify the equation of state of nuclear matter, the dependence of pressure on density under extreme conditions. This is important for understanding neutron stars, black holes, and the early universe. Furthermore, supernovas play a key role in the evolution of galaxies. Supernova explosions eject energy and material into interstellar space. This energy heats the gas and creates shock waves that compress clouds of gas and trigger the formation of new stars. This is called stellar feedback. Supernovas regulate the rate of star formation in galaxies. Without them, all the gas would quickly turn into stars, and galaxies would look quite different. Observations of Betelgeuse will give a detailed picture of exactly how this process occurs. We will see how the explosion energy propagates and how it affects the surrounding gas. This data will help improve models of galaxy evolution. Another aspect is the influence of supernovas on the spread of life. Supernova explosions create and disperse heavy elements necessary for life: carbon, oxygen, nitrogen, and phosphorus. All these elements were created in stars and distributed in the universe by supernova explosions. Without this, life as we know it would be impossible. But supernovas also pose a danger. Hard radiation and cosmic rays from nearby explosions can sterilize planets and destroy life. There is a hypothesis that some mass extinctions on Earth may have been caused by nearby supernovas. For example, The extinction at the end of the Ordovician period about 450 million years ago may have been related to a nearby supernova flare that destroyed the ozone layer and exposed Earth's life to a fatal dose of ultraviolet. The explosion of Betelgeuse will give us the opportunity to study these processes. We will measure the flux of hard radiation and estimate its impact on Earth's atmosphere. Of course, in this case, the impact will be minimal, but we will be able to extrapolate to closer cases. We will understand at what distance a supernova is truly dangerous to life. This is important for astrobiology and the search for life on other planets. If a planet is in a region of the galaxy where supernovas flare up often, its chances of developing complex life decrease. And conversely, regions where supernovas are rare are more favorable. This knowledge will help us estimate the probability of the existence of life in different parts of the universe. Let us also talk about how the explosion of Betelgeuse will be perceived by people without a scientific education, by ordinary viewers. For many, it will simply be a beautiful sight, a new bright star in the sky. People will go out in the evenings to look at it, take photographs, and share them on social media. It will become a topic of conversation, a reason to meet. Families will gather in backyards, gazing at the sky. Parents will tell their children about the stars and space, awakening an interest in science within them. But there will also be those who are frightened. There will be rumors and panic. Some will recall ancient prophecies and see the supernova as a sign of the end of the world. Social media will be filled with conspiracy theories. Someone will say it is not a star that exploded, but aliens launching a weapon. Someone will claim that governments are hiding the true danger and that the radiation will kill everyone. Scientists and educational organizations will have to actively fight misinformation, explain what is happening, and calm people down. This will be a difficult but vital task because panic can be destructive. Fortunately, in the modern world, we have tools for the rapid dissemination of correct information. Science communicators, bloggers, and journalists will be able to promptly convey the facts. Explainer videos will gain millions of views. People will want to understand what is happening, and if the information is accessible and clear, the majority will calm down and simply enjoy the spectacle. For children, this event could be defining. Imagine a child who sees a supernova at 10 years old. This impression will stay with them forever. Perhaps it will inspire them to become an astronomer, a physicist, or an engineer. 20 years later, this person might be among those researching the data from that explosion, building new telescopes, and discovering new laws of the universe. The history of science is full of such examples. One bright event, one inspiring moment changes a person's life, and, through them, changes the world. For culture, the explosion of Betelgeuse will also be significant. It will enter the mythology of our time. In 100 years, people will remember that in the 21st century, a supernova visible to the naked eye flared up in the sky. It will become a cultural marker, a symbol of the era. Artists will depict it in their works, writers will mention it in novels, and composers will write symphonies inspired by the cosmic fire. This event will intertwine with human culture just as comets, eclipses, and other celestial phenomena did in the past. And perhaps this event will make humanity reflect on its place in the cosmos. We live on a small planet orbiting an ordinary star in a corner of the galaxy. The universe is vast, and events of a magnitude before which our concerns seem insignificant occur constantly. But this is not a reason for despair. On the contrary, it is a reason for humility and, at the same time, for pride. We, small creatures, are capable of understanding these magnificent processes. We can observe the explosion of a star, analyze it, and extract knowledge. We can predict what will happen and test our predictions. We are a part of the universe that has become self-aware, and that is amazing. The explosion of Betelgeuse could also become a catalyst for the development of space programs. When millions of people around the world go out into the streets to look at the new star, they will feel a connection to space. They will realize that space is not an abstraction, not something distant and unreachable. It is a reality that can touch everyone. And this realization may push society toward greater support for space research. Imagine that after the explosion of Betelgeuse, governments of different countries decide to increase funding for astronomy. New telescopes are built and new space missions are launched. Young people, inspired by the sight, enter universities for astronomy and physics majors. A decade later, a new generation of scientists emerges, driving science forward. They make discoveries we cannot even dream of now. They find exoplanets suitable for life. They unravel the mysteries of dark matter and dark energy. They perhaps even find traces of extraterrestrial life. All of this can start with one event, with the explosion of Betelgeuse. Because at that moment, space will cease to be something distant. It will become real, tangible, and personal. Everyone who sees the supernova will feel like part of something greater. And this feeling can transform society. Of course, there will be skeptics. Those who will say, "So what? A star exploded. This changes nothing in our lives. We need to solve problems on Earth, not look at the sky." And there is a grain of truth in this. Yes, there are many problems on Earth: poverty, diseases, conflicts, and environmental crises. All of this requires attention and resources. But space does not distract from earthly problems. On the contrary, it gives perspective. It reminds us that we are all on one planet, that our differences are insignificant in the face of the universe. It unites us in a shared experience of wonder. Moreover, space research brings practical benefits. Technologies developed for astronomy find applications in medicine, communications, and energy. Satellites that observe space also monitor the Earth, helping to predict the weather, track climate change, and manage resources. Space and Earth are not opposed to each other. They are connected, and the explosion of Betelgeuse could be the moment when this realization becomes universal. Let us now imagine more specifically how the sky will change after the explosion. In the first days, the supernova will dominate. All constellations will recede into the background. Eyes will be glued to the dazzling point in Orion. But gradually, as it dims, people will begin to notice that the sky has changed forever. Orion is no longer symmetrical. One of its corners shines brighter than before. Even when the supernova dims to the level of an ordinary star, it will still be brighter than the old Betelgeuse, and it will not be red, but white or bluish. The color of the sky has changed. For amateur astronomers, this will be a new era. Everyone will want to point their telescope at the remnant of Betelgeuse. In the first years after the explosion, the remnant will be faint, visible only in professional instruments. But over time, as it expands and interacts with the environment, the nebula will become brighter. In a decade, it will be one of the favorite objects for observation. Amateurs will photograph it, track changes, and share images online. Communities of enthusiasts dedicated to studying the remnant of Betelgeuse will appear. And who knows, maybe in 100 years, technology will allow a probe to be sent to the remnant. The distance of 650 light-years seems insurmountable now. Even light takes centuries to get there. But imagine a ship that can move at near-light speed, or, even more fantastically, a ship using space-time deformation, a warp drive. If such technologies are ever created, one of the first targets will be Betelgeuse. Scientists will want to see the remnant up close, pass through the nebula, collect samples of matter, discover the neutron star or black hole, and study it in detail. Let us imagine once more, but more specifically, the particular night when the explosion occurs. Suppose it is a winter evening in 2026, 2030, or 2050. It doesn't matter. The main thing is that it happens during our lifetime or the lifetime of our children. A family gathers for dinner. It is dark and frosty outside. Conversations flow as usual. Work, school, plans for the weekend. No one is thinking about space. No one is expecting a miracle. Meanwhile, in space, the light wave from the explosion that occurred 650 years ago is crossing the final kilometers to Earth. It is rushing at the speed of light, 300,000 kilometers per second. In 1 second, it can circle the Earth 7 times, and then it enters the Earth's atmosphere. Photons begin to interact with air molecules. The first observers are the automated telescopes that scan the sky every night, measuring the brightness of stars. One such telescope, say in the Atacama Desert in Chile, takes another measurement. The camera records the image. The computer analyzes it and compares it with previous shots. Suddenly, the program sees an anomaly. A star in the constellation of Orion has become brighter, much brighter. The computer checks the data and excludes errors. Confirmation: it is not an error. The brightness of Betelgeuse has increased dozens of times. The system automatically sends an alarm signal. All over the world, astronomers receive notifications on their phones. In California, it is now day. An astronomer at the Palomar Observatory looks at the message. His heart starts to beat faster. Is this it? Is it really happening? He runs to the telescope and begins the setup. In Europe, it is evening. An astronomer at the Paris Observatory sees the notification and cannot believe it. She calls her colleagues. A chain reaction of calls, messages, and emails begins. The astronomical community is in motion, but ordinary people do not know yet. The family at dinner continues their conversation. The child asks for permission to walk the dog before bed. The parents agree. The child gets dressed, takes the dog on a leash, and goes outside. It is cold. The sky is clear, cloudless, and the stars are bright. The child recognizes the familiar constellations. There is the Big Dipper. There is Orion with its belt of 3 stars. But something is wrong. One of the stars of Orion is somehow too bright. The child blinks and looks again. No, definitely. The star in the place of the hunter's shoulder is shining much brighter than usual. Brighter than he remembers. The child stands with his head tilted back, not understanding what is happening. The dog pulls the leash, wanting to walk further, but the child does not move. He looks at the star, and it seems to be getting even brighter right before his eyes. It can't be. Stars don't change that fast, but the fact remains. In the couple of minutes while the child is watching, the star has become noticeably brighter. Now it is the brightest in the whole sky. Brighter than Sirius, brighter than Venus, which is sometimes seen in the evening. The child runs back home, bursts into the apartment, and shouts, "Mom! Dad! Come and look! There's something strange in the sky!" The parents stand up from the table in bewilderment. "What is it?" The child drags them to the window and points. "Look! That star! It's huge!" The parents look, and indeed, a star is shining brightly in the sky that wasn't there before, or was there but not so bright. The father takes out his phone and starts looking for information. The internet is already full of posts. People from all over the world write about the same thing. A new bright star in the sky. What is it? And then the first reports from astronomers begin to appear. Breaking news bulletins. Betelgeuse has exploded. This is the supernova event that has been awaited for decades. It has finally happened. The family looks at the sky again. Now, knowing what it is, they see the star in a new way. It is not just a bright dot. It is a cosmic catastrophe occurring at a distance of 650 light years. A star that existed for millions of years has just died, and they are witnesses to this moment. The mother hugs the child. The father calls friends and neighbors. "Have you seen it? Look at the sky." People come out of their houses. Across the street, across the city, across the country, across the whole world, people go out into the streets and look at the sky. Some bring binoculars. In the binoculars, it is visible that the new star is not a dot, but a small disk. It is already so bright that its size can be distinguished. This is striking. Stars usually look like dots even through telescopes because they are too far away. But this star, the supernova, is so bright that its size is visible. A storm begins on social media. The hashtag Betelgeuse becomes the most popular in the world. People share photos and videos. Someone films a time-lapse showing how the star becomes brighter with every hour. Astronomers give interviews on television, radio, and the internet. Everyone wants to know what it means. Is it dangerous? No, scientists say. It is safe. The distance is large enough. Enjoy the spectacle. This event happens once in 1,000 years. The night passes. By morning, the new star is visible even at dawn as the sky lightens. It shines against the background of the pale blue sky. People go to work and school, but everyone constantly glances at the sky. Someone stops on the street and points a finger. There, you see. Strangers talk to each other, discussing the phenomenon. The usual barriers of social convention recede. Everyone is united by the shared experience. In schools, teachers cancel lessons and lead the children outside to show them the supernova. They talk about stars, life cycles, and how elements are created in explosions. The children listen with bated breath. This is not abstract knowledge from a textbook. It is happening right now, here, in the sky above their heads. They are seeing science in action. By the evening of the next day, the new star has become even brighter. Now it shines with approximately the brightness of a full moon. At night, one can read by its light. The shadows from it are sharp and clear. People walk through the streets, and they do not need flashlights. The light from the supernova illuminates everything around. It is a strange, surreal sensation. The sky is not black, but dark blue. The stars pale against the bright light of the new star. The Milky Way is almost invisible. All attention is fixed on one point, on Betelgeuse. Animals behave strangely. Birds that are usually silent at night begin to sing, thinking that dawn is coming. Dogs howl, looking at the sky. Cats sit on windowsills, staring fascinated at the new star. Even wild animals in the forests feel the changes. Night predators come out earlier than usual, disoriented by the unusual light. Nature feels that something unusual has happened. Astronomers do not sleep. They work around the clock, taking spectra, measuring brightness, and tracking changes. Every hour brings new data. The spectrum changes, showing various elements. The expansion speed of the shell has been measured, tens of thousands of kilometers per second. This matches the models. But there are surprises too. Some lines in the spectrum are unexpectedly strong. This indicates that the synthesis of certain elements was more intense than the models predicted. Scientists will have to figure out why. Neutrino detectors confirmed that there was a powerful burst several hours ago. Thousands of neutrinos passed through the Earth, and detectors recorded hundreds of collisions. This is a record. Never before have so many neutrinos from a supernova been recorded. The data is being analyzed. It will tell about what was happening in the star's core at the moment of collapse, about the temperature, density, and dynamics of the process. Days pass. The supernova's brightness reaches its peak and begins to fall slowly, but even after a week, it is still the brightest object in the night sky after the moon. People get used to the new reality. Every evening they go out, look at the sky, and check, still there, still shining. Gradually, it becomes part of life, a new star in the sky. Children born at this time will grow up seeing it. For them, it will be normal. They will not remember the sky without the supernova. After a month, the brightness of the supernova has dropped significantly. It no longer illuminates the night like the moon, but it is still one of the brightest stars in the sky. And in the telescope, something amazing is now visible. Around the central bright point, a faint shell has appeared, an expanding nebula. This is the gas ejected by the explosion, now cooled and glowing with its own light. The shell grows. With every day, it becomes larger. Professional telescopes take detailed images showing structures, filaments, nodes, and inhomogeneities. The shell is not perfectly round, it is asymmetrical, just as the models predicted. Astronomers measure the chemical composition of the shell. The spectra show lines of oxygen, carbon, silicon, and iron. This is confirmation. We are seeing the insides of the star, layers that were once hidden deep under the surface. The explosion turned the star inside out and scattered its insides into space. These elements will someday become part of new stars and new planets. Perhaps in billions of years, a planet will form from this material on which life will arise. And that life will consist of atoms born in Betelgeuse. After 3 months, the supernova has dimmed to the level of an ordinary bright star. It is still visible to the naked eye, but it no longer dominates. The sky gradually returns to normal. Other stars become noticeable again. The Milky Way is visible again in dark places. But the shoulder of Orion has changed forever. Instead of the reddish Betelgeuse, there is a bright white star. The constellation looks different. Astronomers update star maps and atlases. New editions of books about constellations show Orion with a changed shoulder. In a year, the supernova is visible only through binoculars or a small telescope. For the ordinary observer, it has merged with the general background of stars, but astronomers continue to follow it. Every night, dozens of telescopes around the world are pointed at the remnant of Betelgeuse. Data accumulates. Every spectrum and every image adds a detail to the general picture. Scientists write articles. In the first year after the explosion, thousands of scientific papers about Betelgeuse are published. It is the most studied supernova in history. In 5 years, the remnant of Betelgeuse is visible only through professional telescopes, but in them, it is magnificent. The nebula has expanded to a size comparable to the visible size of the moon in the sky. Of course, it is much fainter, but through powerful telescopes, incredible details are visible. Colors: red from hydrogen, green from oxygen, blue from hot gas. Structures: spiral waves, shock fronts, and bubbles. It is one of the most beautiful objects in the sky. Amateur astronomers all over the world point their telescopes at the remnant. They take long exposures, accumulating light for hours. The result is stunning images which are then published on the internet. Communities of astrophotographers thrive. Everyone wants to capture the remnant of Betelgeuse in their own way, to find a unique angle and highlight details. This becomes something of an art. Scientific photography turns into an aesthetic experience. In the center of the nebula, scientists try to detect the core remnant, a neutron star or a black hole. This is a difficult task. The center of the nebula is bright. There is a lot of hot gas glowing in X-rays. X-ray telescopes record powerful radiation from the central region, but isolating the signal from the core remnant itself is not easy. Data analysis takes years. 10 years after the explosion, a publication finally appears. A pulsar has been discovered. In the center of the Betelgeuse remnant is a rapidly rotating neutron star. It makes 100 revolutions per second and emits beams of radiation that, like a lighthouse, rotate with it. Radio telescopes record regular pulses with a period of 0.01 seconds. This is the Betelgeuse pulsar. It becomes one of the most studied pulsars. Astronomers measure its magnetic field, the rate of rotational slowdown, and the radiation spectrum. All this data helps to understand the physics of neutron stars. But the story of Betelgeuse does not end there. The nebula continues to expand. Every year it becomes larger. 100 years after the explosion, it will occupy an area in the sky the size of several lunar disks. Of course, it will be faint, visible only through telescopes, but for astronomers, it will remain an important object because it is close, because we observed it from the very beginning, and because we have a full set of data from the moment of the explosion to the final stage. The interaction of the expanding shell with the surrounding nebula will continue for centuries. The shock wave will compress the gas, heat it, and trigger the formation of new stars. In the vicinity of the Betelgeuse remnant, new suns will ignite in millions of years. They will consist of material enriched with heavy elements from the explosion. Planets will form around these stars. And who knows? Maybe life will arise on one of these planets. Life consisting of Betelgeuse atoms. And what about humanity? How will the explosion affect us in the long term? Firstly, it will be a powerful educational impulse. Children who saw the supernova will grow up with a deep interest in space. Many of them will become scientists, engineers, and researchers. They will drive science forward, make discoveries, and build ships that will someday reach the stars. Betelgeuse will become a source of inspiration for an entire generation. Secondly, it will strengthen international cooperation in science. The explosion of Betelgeuse is an event that recognizes no borders. It affects everyone regardless of nationality, religion, or political views. Astronomers from all over the world worked together, shared data, and discussed results. This experience of cooperation could become a model for other areas. If scientists can work together on studying space, why not apply the same approach to solving earthly problems? Thirdly, it will change our worldview. We have seen in practice that the universe is dynamic, that stars are born and die, and that everything is temporary. This can make us more humble, but also more appreciative of the moment. If even giant stars are not eternal, then how valuable is every minute of our short lives? This is a philosophical thought, but it can have practical consequences. People may begin to value what they have more, care for each other more, and think more about future generations. Of course, all this sounds optimistic, perhaps too optimistic. Reality is always more complex, but even if the explosion of Betelgeuse has only a partial influence in this direction, it will already be a huge achievement because space has the power to change us. When we look at the stars, we see not just dots of light, we see our history, our origin, and our future. We see where we came from and where we are going. Betelgeuse, by exploding, will give us a lesson. A lesson about cyclicity, about transience, and about the beauty of the temporary. A star that shone for millions of years disappeared in an instant, but it did not disappear without a trace. It left offspring, atoms scattered in space that will become part of new worlds. It left a legacy, knowledge that we gained by observing it. It left a memory in our hearts, in our culture, and in our stories. Imagine, in 1,000 years, when people or their descendants, perhaps already changed beyond recognition, look at the sky. They will see the remnant of Betelgeuse. They will know the story of how in the 21st century, or whenever it happens, their ancestors observed the explosion, how it affected society, and what discoveries were made. This story will become part of the collective memory of humanity. Just as we now remember the supernova of 1054 observed by Chinese astronomers, so too in 1,000 years will Betelgeuse be remembered. And perhaps by then, humanity will already be an interstellar civilization. Ships will fly between stars, colonies will be scattered across the galaxy, and one of the stops on interstellar routes will be the remnant of Betelgeuse. Tourist ships will bring people to see the nebula up close, pass through the expanding layers of gas, and see the pulsar in the center. It will be a monument not to someone's victory or achievement, but simply to the fact of existence. A monument to a star that lived and died, as everything in the universe does. But for now, that is far off. For now, we are here on Earth, waiting for the sky to change, waiting for the light from the explosion, which perhaps has already occurred, to reach us, or waiting for the explosion to occur in the future. We do not know, and this ignorance makes the waiting sharp and exciting. Every night is a possibility. Every time we look at Orion, we check if it is still there. The reddish shoulder of the hunter still flickers in its place. For now, yes. But someday the answer will be different. Someday we will look and, instead of the familiar red star, we will see a dazzling flash, and then a new era will begin. The era after Betelgeuse.